This presentation is actually part 6 of the Nova East Special Speakers Series. It will be, as you know, this whole session is being recorded. It will be part of this recording, but it'll also be a separate entity under the Nova East presentations on the RASC YouTube site. Pat is a longtime member of our center. He has served many roles on our board, certainly been an active observer. He's currently our National Council representative and sits as a director on our board. And if he doesn't have a pair of binoculars out at the night sky, he's out there during the day looking at birds. So he's constantly got something up here. But today, because of the prominence of Mars in our viewing coming up and now, we've asked Pat to do this presentation. So Pat, thank you so much for this, and take it away.
I even remember to unmute first this time. Okay, so I assume at some point, oh, yes, the share screen's down at the bottom. And right. I think we should be good to go. I'd like to thank Judy for, Dave Chapman actually, who originally sort of twisted my arm to give a talk as part of the COVID-19 version of Nova East. And I originally had made this talk a little bit on the shorter side. Well, it was a bit longer, but then I thought, it's not a standalone talk anymore. And I actually heard somebody use a term I'd never heard the other day, which is Zoom bottom, which is when your butt gets sore from sitting through too many Zoom presentations. So this is going to be a little bit shorter than the over 1 hour ones that some of the other ones have been. At least I'm going to try and keep it to that. And basically the reason why Mars is of great interest to a lot of people is because it undergoes an opposition on occasion. And so I thought what I'd do is I'd talk about why we have oppositions, what oppositions are, why Mars is so special, and a bit about what you might want to learn about how to observe it during this, because I made some really bad mistakes when I first observed my very first opposition of Mars. And by opposition, most people, when they hear the word opposition, they think of those people in Parliament that start whacking the desks with their hands and making weird grunting noises. It's not that type of opposition. Opposition is an astronomy term, and astronomers tend to get excited over them, especially the oppositions of Mars. And these oppositions only happen to superior planets, which are the planets that actually have orbits bigger than the orbit of the Earth. So if you actually sort of take a look at a little schematic diagram of what the solar system looks like, we have the sun at the center, we have the Earth, which is over here, moving around the sun in a circle and moving along in a reasonably good eclipse. So the little arrow there just shows you that we're moving, that's just an arbitrary length. It just shows that we're moving. And outside the orbit of the Earth, we have superior planets moving in their orbits. And the funny thing about superior planets, whenever you see a diagram about oppositions, the superior planet they always show is red. I've very rarely seen a diagram where it's not red, because usually Mars is the one that people are most interested in. And as you can see, one of the interesting things about our solar system and the way that gravity works is that the further away you are from the sun, you move around the sun more slowly, and you have a much bigger orbit in which to go around. So you're not only moving slower to start with, you actually have a much bigger distance to travel to go all the way around once. And as I mentioned, the planets that actually do this, the ones that we actually have to deal with in orbit, in order coming out from the Earth, we have Mars, which is the closest planet, and then we have the Jupiter, Saturn, Uranus, and Neptune. And those are the 5 planets that actually can have oppositions. And what I'm going to sort of show you is a bit about why these oppositions occur at the rate that they do, and why in particular Mars makes such an interesting one to look at. So in the diagram, you saw that Earth, actually if I just back up for a second, you can see that opposition occurs at the point where the Earth lies between the sun and the superior planet. So once you have one opposition, the Earth continues merrily along its way. The superior planet, i.e. Mars, also continues merrily along its way. So one of the questions is, once you have an opposition, how long does it take until you have the next opposition of the same planet? So that is, when you look at the 5 superior planets, it brings in a term called the synodic period. And the synodic period is basically how long it takes the sun and the Earth and a planet to go from any given arrangement back to the same arrangement. So from one opposition to the next opposition is the synodic period of the planet. And it comes from the word meaning synod. Most people, the only place you'll ever come across the word synod is it's a gathering of the hierarchy of a church, is usually where you end up hearing with a synodic council or something. And it means a getting together. And in this case, they're getting together in a line with, again, as you can see, this caption says it's for a superior planet. Note that the planet is red. So what you're going to see when I run this little illustration is you're going to see we're going to start off with opposition. The Earth continues on, and as I mentioned, the other planet continues on, but it's moving slower. And as a result, by the time the Earth catches up to it again, you can see that the synodic period, how long it takes the Earth to go around till it's lined back up at opposition again, it's always going to be longer than a year. Because during the first year that goes around, the planet has moved a bit. Now, the farther out it is in its orbit, the slower it's moving and the bigger its orbit has to be. So the synodic period gets closer and closer and closer to a year as you go further and further out into the solar system. So if we take a look at the 5 planets that have superior orbits and that therefore have oppositions and look at their synodic period, if you take a look at Neptune, you can see that Neptune's synodic period is 368 days. In other words, it really doesn't go very far in the time it takes the Earth to go around its orbit once. Now, the next planet in, Uranus, doesn't do much better. We only have to go an extra 2 days in order to catch up with these planets. So their oppositions tend to come around at almost the same time every year. They're a few days later, but they don't change very much from one year to the next. You just get a few days later, a few days later, a few days later. And if you go back through a stack of observers' handbooks and look up, say, the date of the opposition of Neptune in 1 year, it's going to be very easy to find the next year. Go to the same month and look a few days later, and you'll find it. It doesn't move all that far. You come a little bit closer, and Saturn, it's still only up 10 days compared to what it was for Neptune. Now, when you come into Jupiter, now we're starting to get somewhere. Jupiter is close enough that its orbit is smaller and it's moving faster, that its synodic period is just under 400 days. Now, since the year has about 365, that's about 30 days. I'm just going to round off to 30 days. 30 days is about 1 month. So in the case of Jupiter, once you have an opposition of Jupiter, the next opposition is going to happen 1 month later. And since there's 12 months in the year, and 13 officially zodiac constellations, if you look at Jupiter, every year its opposition moves it on average from one constellation to the next. It moves along at a fairly good clip. So what about Mars? Well, Mars is quite close to the Earth, so it's moving not that much slower, and its orbit is bigger than the Earth, but it's not that much bigger. So in the case of Mars, the synodic period is 780 days, which is over 2 years. So if you take a look at that, I'm going to get back to this, the fact that it's over 2 years in a bit, but that's one of the main reasons why oppositions of Mars are greatly looked forward to with anticipation, is because they only come roughly every 2 years. In fact, it's 2 years and a bit. So unlike the other planets, you know you're going to get one, if you have an opposition of Jupiter in July, next year it's going to be in August. So you just wait a year and a bit and you've got it. Mars, it's not quite so simple. You've got to wait 2 years plus a bit. Now, for all the planets that are superior planets, as the Earth moves around in its orbit, if we just assume that the superior planet is just sort of staying there, or if it's, for example, a superior planet like Neptune that doesn't really move very much in the amount of time it takes the Earth to go from here around to here. So this would be the planet at opposition when we're closest to it. And around here is when we're just coming around from the sun and we have a clear view to it again. And as you can see, the Earth is going to be closest to a superior planet when it's at opposition. And when it's on the opposite side of the orbit, it's not as close. So as the Earth goes around in its orbit, from synodic period to synodic period, the distance to the planet changes. And what the distance to the planet does is it changes two of the observable object properties of that planet. In particular, it changes its apparent size, how big it appears when you look at it through a telescope, and it also changes the brightness of it as you look at it even just with your naked eye. it's noticeable for some of these. So if we take, for example, a look at apparent size, and again, I'm going to start off with the outer part of the solar system. As you can imagine, Neptune is very far away from the sun. So the distance from the Earth to Neptune is not going to change very much regardless of which size of the Earth's orbit it's on. So in the case of Neptune, the angular size of the planet as seen from Earth goes from 2.1 arc seconds when it's at opposition, or when we're just coming around the sun and can see it, to 2.3 arc seconds when it is at opposition. So not really a big change, and that's to be expected. For those of you who want to get an idea of just, I've actually used real units here. In fact, there's 10 arc seconds, there's a pixel for every arc second in these images. But to just give you an idea of just how small these angles are, 1 degree is divided into 60 seconds. So if you imagine taking a protractor that you had when you were in school, that was usually marked off in 1 degree increments around the outside, take each of those, divide into 60 smaller units. Those are arc minutes. Then take one of those little tiny subdivisions and make it into 60 even smaller units. Those are arc seconds. So there's 3,600 of these arc seconds in 1 degree. And to give you an idea of just how small an arc second is, if you take a $2 coin, which I imagine most of you may have handy, if you take a $2 coin and place it 5 kilometers from you, and then look at the angle from one side of that coin to the other, not the not thin on, but look, say you're looking at the polar bear face on, 1 arc second is the angle from one side of the coin to the other. It's a very small angle. And in fact, I'm actually amazed that astronomers with modern technology can actually measure micro arc seconds, which would be literally like being able to see the fur, the hairs in the fur on the polar bear from 5 kilometers away. That's an amazing sort of thing of measurement. If we come into Uranus, it's a little bit closer to us, so it appears a bit bigger than Neptune does. But again, because it's so far out, its angular size doesn't really change that much. It goes from 3.3 to 4. Now, Saturn is a much larger object. But again, it's still far enough away from us that in the difference from when we see it just coming around the sun to when we see it at opposition, it doesn't get that much bigger. In fact, generally, most people tend to notice more about Saturn is that instead of its actual size or apparent size, is the tilt of the rings. That's usually the thing that really stands out for people as we look at it over extended periods of time. It's the changing angle of the rings going from full on to thin to full on again that people generally tend to notice more than they notice that it looks a little bit bigger than it did 5 months ago or 6 years ago or whatever it was. Now, Jupiter, as you can imagine, is going to look even bigger than Saturn. And this is Saturn, Jupiter to scale. You can see that it's much larger in angular size than all the other planets. These are all actually at the same relative measurements. But even Jupiter only goes from 30 arc seconds up to about 50. So it doesn't even get twice as big when it comes up to opposition. So why is it that Mars is the one that causes all the concern? This is why. Mars actually gets 7 times bigger from the time we can see it when we come around the sun or before it disappears behind the sun to opposition. And as you can see, it gets almost as big as Jupiter at its smallest. So if you want to see a lot of detail or a lot of surface features on Mars, the time to do it is at opposition when it is a really, really large object. Okay. So over the last 6 months on either side of the upcoming opposition, this is a little diagram that I found online. This shows what Mars looks like from Earth. And as you can see, on March the 20th of this year, it was relatively small. In March 21st of next year, it's going to be relatively small. And you're almost here. When it's opposition, it's going to be that big. And that's why oppositions of Mars are such a really, really big thing. It's because you get to see lots of detail with even a relatively small telescope and relatively low magnifications compared to what you need at other times of the year. Now, I also mentioned brightness as one of the other things that changes things for Mars. And this is a diagram that was in the 2020 Observer's Handbook. One of the nice things that I'm able to do is because I'm the one that provides the diagram, is I can go in and change it around any way I want. So I've stripped out a lot of the stuff and left only the three visible superior planets. So Mars, Jupiter, and Saturn. And as you can see in the case of Jupiter, Jupiter had its opposition back in July. So Jupiter's brightness gradually increased and gradually increased, and it reached a maximum in the middle of July when it reached opposition, and then it sort of faded away again. But notice that it doesn't really change in brightness that much, and that's because, if you remember from the diagram, Jupiter's size doesn't really change all that much. Same thing with Saturn. Here we have Saturn. It gets somewhat brighter at opposition, but fades again afterwards. But again, it's not a huge change in brightness. In fact, I suspect if you actually worked it out numerically, you might find that the actual brightness of Saturn is more dependent on how open its ring system is than how close it is to the Earth. I didn't actually do that, but that would be my first guess. And then you can see Mars. Mars comes out at the start of this year out of nowhere. And you can see that as it comes up to opposition, its brightness goes way up. And then after opposition, its brightness is going to go down just as quickly. And as Dave pointed out, it's almost as bright as Jupiter. And it's not quite as bright as Jupiter, probably because it's not quite as reflective of a surface, and also because it's not quite as big as Jupiter. And Jupiter is near its opposition right now. And if you're wondering, just to give you a comparison, Venus would be running around in the upper part of this diagram. So Venus is still by far the brighter of the planets. But as you can see, Mars puts on a real show when it comes up to opposition, and then it very quickly sort of tends to disappear again. Okay, I'm going to go back to this idea of how long Mars' synodic period is, because I'm then going to show you a diagram that's in the handbook that, like most things that Roy Bishop produces, is very dense in information. So I mentioned that the synodic period is about 780 days. And if you break that down, that's 2 years plus about 50 days. So you notice that unlike Jupiter, it's about 1 year plus a month, in the case of Mars, it's 2 years plus almost 2 months. And what that means, and again, if you look in the Observer's Handbook, you're going to find this diagram. There's a lot of stuff in this diagram I'm not going to bother with, because I just want to point out some of the main things about it. So here we have the sun at the center. Here we have the orbit of the Earth, and the months along here indicate which month it is if you're on the Earth. So if the Earth is over here, it's November. If the Earth is over here, it's December, and so on and so on and so on. Out here we have the orbit of Mars, and next to the orbit of Mars we have the constellation it's in. So if Mars is here, it's in the constellation of Aries, which is a winter constellation. If it's over here, it's in Cancer, which is a spring constellation, and so on. And then there's 4 diagrams that sort of show Mars, and the size of the circle, the big circle, is its maximum angular size in arc seconds. You can see over here it's 24, which is what we're sort of gearing up to a little bit. And then the other thing about this diagram is you notice that it's indicated in here with lines when the oppositions of Mars actually occur. So over here we have the one in 2018, and you notice that the one from 2018, the next one, this one in 2020, is 2 years, so 2020, plus start of August, start of September, right there. So 2 months and a bit. And the next one is going to be in 2 years, 2022, and again about 2 months. The next one is going to be 2 years, but that extra 2 months adds up. So every 5 synodic periods, you have to throw an extra year. And you'll see what happens here is this one goes from here. We've switched over into January. This one occurs in 2025. And then the next one is in 2027 when Earth is here and Mars is here. 2029, Earth is here, Mars is here. 2031 and 2033. So the diagram that's in the handbook shows you all of the oppositions of Mars, as the title says, from 2018 to 2033. And you can really easily see from this diagram how elliptical Mars's orbit is. So if you look, for example, at the orbit of the Earth, it looks pretty circular, whereas you can clearly see that Mars is closer to the Earth, or closer to the Sun on this side and farther from the sun on this side. So you think, okay, well, ideally, what you're going to want is you're going to want to have oppositions when Mars is over here at its closest. Okay, there's problems with that, though. The first problem is we're viewing it from Nova Scotia. So when the oppositions occur when it's really south, so I've got a diagram here that sort of shows the southern sky is seen from Nova Scotia. Here's Scorpius down here, just to sort of give you a bit of an idea what you're looking at. This is Sagittarius. This is the east, this is the west, and this is the celestial equator projected onto the nighttime sky. And this is the zenith right over here. So this is the point looking straight up overhead. And here we have the ecliptic. This is where the planets are found. So if Mars happens to be in this particular part of the sky, and this is actually on the June solstice, objects in the sky tend to circle. They rise, they cross the sky, and they set in the west. And you'll notice that if you have a planet like Mars that happens to be here, it's going to rise, come up as far as there, which is not very high above the horizon, and set in the west. So it's not really going to get all that far above the horizon at our latitude. And in the summertime, as you're probably well aware, you tend to have a lot of haze in the sky. You're looking through a lot of this atmosphere. And that turbulence, by looking at that extra atmosphere, is going to degrade the seeing, which determines how sharp a view of the planet you're actually going to get. So we think, okay, well, that's fine. Are there any other problems with observing when they're really close? Yes, there is. So here's the Earth and here's Mars at the actual right relative sizes to show you how large one is compared to the other. And both of these planets, just by coincidence, happen to have inclinations that are almost exactly the same. 23.5 degrees for Earth, 25.2 degrees for Mars. And what that means, as we know on Earth, is that as the Earth goes around the sun, we get summer in the northern hemisphere, and then we get winter in the northern hemisphere. The same thing happens for Mars. When Mars is on one side of its orbit, the northern hemisphere gets a lot more sunlight than the southern hemisphere does, and vice versa. So why is that a problem? Well, if we go back to this diagram, you see this big circle up here? This circle shows you the size and extent of the northern ice cap on Mars. And if Mars is over on this side of its orbit, where it's closest to the sun, it's summertime in the southern hemisphere of Mars. Here's the northern ice cap. It's nice and big. And you can see on the opposite side, the northern ice cap is now getting a lot of sunlight, and it's much, much smaller. Now, why would that be a problem? Well, one of the problems is that because the southern hemisphere gets a lot of extra sunlight during the summertime, that extra heat drives winds that are much stronger typically than they are during the rest of Mars's orbit. So when you tend to have Mars at the point in its orbit where it's really close to us, you also have the risk of planet-wide dust storms, which blot out all of your detail. Now, for those of you who think dust storms on Mars are anything at all like the ones depicted in the book or the movie The Martian, I hate to bring the bearer of bad news to you. There are dust storms on Mars. It does raise lots of dust blocking the view. It does not blow you off your feet or destroy your base or anything else that's described in The Martian. I've read the book, and the author freely admits that he couldn't have written the book if he didn't really overdo the winds on Mars. The rest of the book, if you're a geek at all, the rest of the book is an amazing read. It goes into a lot more of the science and exactly why and what happens and the scientific reasons why the guy does what he does in order to try and keep alive on Mars. But Mars's atmosphere is only 1% the thickness of Earth's atmosphere. And the force of moving gas depends on the speed and it depends on its density. So a 100 kilometer per hour wind on Mars is the same as a 1 kilometer per hour wind on Earth. And I don't know anybody who's ever been blown off their feet by a 1 kilometer per hour wind on Earth. So he freely admits he had to do that to get the novel started, but once it gets going, the science in it after that is really quite good. So that's another reason why you might run into a problem. You might want to say, well, that may not be the best time to actually have oppositions. Okay, Well, what about oppositions when Mars is as high above the horizon? That gets rid of the problem that we have with all of the looking through all that dense, mucky atmosphere. So here we have the winter solstice in December. Here's Orion, there's Sirius, there's Gemini. Again, the white line is the celestial equator, going from one side to the other. The yellow line is the ecliptic, the place where you're going to find the planets. And as you can see, if you're a planet, you're going to come up, you're going to rise across the sky, and you're going to get almost overhead. You're getting really, really high in the sky this time of the year. So you would think, well, that's got to be a benefit. But there is one drawback. So if we go with the other side, the drawback, there's twofold. First of all, when the ecliptic is really, really high, Mars is at the far point in its orbit. So the biggest it gets is nowhere near as big as it gets when it's over on this side of its orbit. So even in opposition, although Mars gets bigger, it gets not as big as it does because its orbit is highly elliptical. The other problem with this time of the year is it's bloody cold. So if you want to go in January or February, when Mars is up really high in the sky, you can, but the observing conditions aren't nearly as conducive to relaxing as they are in the summertime when you're looking through all that muck. So you would think then that the obvious compromise is going to be the other two sweet spots on either side, which are a compromise between distance of the planet at opposition and a fairly good elevation and reasonably good weather. And if you look, you'll see that the 2020 eclipse, or the 2020 opposition, and the next one in 2022 are both sort of in this neck of the woods. This one in particular, because October is actually quite a pleasant time in terms of weather. And if you look at where it's going to be in the sky, it's going to be about here. And therefore, as it goes across the sky, it's going to stay relatively high up above the horizon. So you get the best of both worlds. Relatively high elevation, fairly large diameter, so you can actually see it well, and relatively pleasant weather for all of that. Now, the other thing that often comes up is what time of the night is best for observing Mars when it's around opposition? And the answer to that is all night. Start when it's low in the east and keep observing until the sun comes up. And I'm going to show you why that is the case. So I use Voyager, the program, one of the programs that I use on my computer, to show what Mars is going to look like at midnight. So at midnight, it's going to be as high in the sky as it's going to get on October the 13th. And if I could see this detail in my little telescope, I would be very happy. In fact, I'd actually be worried that there's something wrong with my telescope or my eyesight. But you can see that there's going to be detail visible on Mars. And I'm going to show you Mars at midnight for a sequence of days. Sequence of hours, actually. And there's two things you're going to notice. One is you're going to be able to see Mars's rotation. And the other is you're going to see something else that is going to happen if you're like me, or if you have any telescope that uses an azimuth mount. So I just want to let you be aware that this is going to happen, and so you're not wondering what the hell is going on. Okay, so here's what it looks at midnight. This is what it's going to look like at 1 o'clock in the morning. Now, if you go back one step, look at this marking here, and look at this marking here. And in the 1 hour from midnight to 1 o'clock, you can see that they've moved this way. So the planet, as seen from Earth, is rotating in this direction. It's rotating clockwise. 2 o'clock in the morning, that rotation continues. But you may have noticed something else is happening, especially if you've been looking. I'm going to just back up. Look at the South Polar Cap. Remember, it's somewhere in the southern hemisphere. So this is the southern ice cap, and it's very, very small now because it's summer. But you may have noticed that it's moving. It's not rotating with that in the same place. It's moving as well. Okay, so this is 1 o'clock. This is 2 o'clock. This is 3 o'clock, 4 o'clock, and 5 o'clock. So you'll notice that the rotation is fairly obvious. It's rotating in this direction, but the entire disk is also rotating, so that now the little ice cap is up there. What's that all about? Well, clearly the obvious rotation that you're seeing here is rotation because Mars is rotating on its own axis. This extra thing is because if you're looking at it with an alt-azimuth telescope, as it moves across the sky from being high in the sky to being low in the west as it starts to set, it rotates. And we don't usually think of that as being something when you're looking at a planet, but we're very familiar with it from something like Orion. So when you see Orion rising, Orion rises more or less on his side. And then as Orion goes up into the sky, when he's due south, he's standing up nice and high. And then as he goes to the west, he's turned around. So you can see that from up to the top to going down to the south, it rotates almost through 90 degrees. Mars will do the exact same thing. And if you're using an alt-azimuth mount, it looks like the planet is rotating in your field of view. So don't think that there's something weird going on. It's just that type of mount is going to give you that sort of effect. Now, the other thing that I mentioned is there's something else that's going to happen as well. And I've got the standard disclaimer. There's going to be a little bit of reading ahead. I'm going to go back to that rotation period. Earth rotates every 24 hours. Now, Mars, just as Mars is tipped over at almost the same angle as the Earth, Mars also rotates in almost the exact same amount of time that the Earth does, but it takes Mars 24 hours and 37 minutes. So that means that Mars rotates more slowly than the Earth does. Now, why is that something you really need to take into account? And this is where the block of text is. So because Mars rotates more slowly than the Earth, at the same time the next night, after 37 minutes, you'll get the exact same view of Mars. And I'll show you that. Okay? So here, I'm going to go back to October the 13th at midnight. And you may recall that the last time around, as we went from midnight to 1 to 2 to 3, this thing moved in this direction because that's the direction in which Mars is actually rotating. Right? There's one pole. The other pole you can't see, but it's rotating this direction. So what happens if you just wait till the 14th and go out and look at Mars again at midnight? Notice that this bar has moved in the opposite direction. You're going to have to wait another 37 minutes while Mars completes one of its rotations to get back to this view, which is the same view you had the night before. And in fact, for every day you wait, so this is on the 14th, if you wait until the 15th and say, I'm going to go right to the 13th, well, 13th is fine. I looked at Mars. 14th is cloudy. I'm going to go to midnight on the 15th. On the 15th, you're going to have to wait 37 minutes plus another 37 minutes before you see the exact same view of Mars that you saw on the 13th. Now, back in 1988, when there was an opposition of Mars, I had no idea that this was an issue. So I had my telescope and I made a sketch on September the 28th, and it's a pretty crude sketch, but I'm not going to be anywhere near the artistic ability of a lot of people. But you can see there's an ice cap. There's a dark area, and here's a dark area with the long dark area sticking in there. And I thought, oh, that's great. And I don't know if I was either busy the next night or it was cloudy the next night. But the night after that, I went out again. Now, the seeing was better that night. But again, there's the ice cap. There's the dark thing. There's this thing. And I thought, well, oh, that's great. I got a better sketch of it. And if that's all I'm ever going to see of Mars, I'm going to put the telescope away. I'm not going to go and take a look at Mars anymore, because that clearly every night I go out, that's the only part of Mars I'm going to see. And it never even occurred to me to get up at, well, anyone who knows me knows I don't normally get up at 4 o'clock in the morning anyway, unless it's to make a quick trip to the bathroom or unless there's a really amazing comet. But it never even thought to me to get up 4 or 5 hours later and see if the view of Mars was different. And if I had, I would have kept on sketching different parts of Mars. Now, that type of sketch, you might think, oh my heavens, that must be a really big telescope. No. This was the telescope I was using, a 60 millimeter refractor. Now, granted, it's one that's got a metal tube and glass lenses, as opposed to the ones you get nowadays, which are all plastic. And And in fact, in terms of David's talk earlier, yes, it did come with an actual solar, it came with a solar projection system, but it also came with an eyepiece that actually had a solar thing on it. And it didn't even go in the end of the eyepiece. You simply screwed it on over the end and you looked through it. And I did that on numerous occasions when the sun was very low near the horizon and for no more than 5 seconds at a time, just to prove to myself that there were such things as sunspots. I realize now that I probably should take the thing and just throw it right in the garbage. But even with a small telescope like this, you can actually see a huge amount of detail on Mars if you have reasonably good seeing. And we have a few members. Mike Gatto posted this picture that he took a few days ago. I corrected it from the universal time that Roy posted into our time, which is 6 o'clock at 4:30 in the morning. Again, I would normally think to get up at 4:30 in the morning, but this is the sort of thing that you can get if you spend some time looking at Mars. And as Michael points out, he first did a pencil sketch of it to get the shading and everything correct, using relatively high magnification, and over a period, I think he said about an hour. And then after he had done that one, he then later added the coloring to it. But this is the sort of thing that you can see. Now, he was using a bigger telescope than mine, but bigger telescopes bring in their own problem. And so the last thing I want to talk about is filters. If you have a really big telescope, because Mars is so incredibly bright, you may find it dazzlingly bright. So one of the ways to fix that is to get a neutral density filter to put over your eyepiece, which will dim the imaging down. It dims everything equally, so the color rendition, everything stays more or less the same. But it does mean that if you have a really big telescope, you can actually look at it and not be dazzled too much by the brightness of what you're looking at. This is one option. So this neutral density filter just sort of screws into the end of your eyepiece, and they come in different levels of density. The other option you have, and I didn't bother taking a picture of it, is you can also use what's called an aperture stop, which is basically a covering that goes over the big end of your telescope with a smaller hole in it to block most of the light, so that you're not getting all the light from the telescope. That also works. In fact, the one that I have, one of the materials that's really good for making aperture stops, if you have a big Dobsonian like I do, is that that corrugated plastic stuff that for sale signs are made from. You know, 2 sheets of white of plastic with a corrugated part in the side. Mine's actually cut from a John Buchanan election sign from the very last election he was in, because he'd already said he wasn't going to be running, and there were a few of them still sticking around. I said, I'm going to help grab one of those and turn it into an aperture stop, and I still have it to this day. The other thing is that for some people, color filters can also be really good at bringing out extra detail. The handbook recommends reds and yellows, but you can try other types of eyepieces or eyepiece filters. These generally just sort of, again, they just sort of screw in at the back of the eyepiece. And one of the advantages these tend to do as well is generally these will also act as a neutral density filter. So they'll block enough light as they let through just the particular wavelengths of light that they normally let through mostly, so that you'll actually get a dimmer view. So that seems to work out well. And often the reason for this is because Mars's atmosphere does tend to backscatter some blue. So you can get rid of that blue to see what's on the surface through it by using either reds or yellow filters. So I'm open to any questions if anybody has any. I think I probably do a stop share so I can see everything else.
Yeah. Bob Russell asked, you mentioned larger telescope aperture. Could you define larger?
I would say 20 centimeters or 8 inches if you're using the old system. Anything generally above that is going to might give you a problem. So if you've got a 16-inch telescope and you're looking at Mars, it's probably going to be bright enough that you're going to have trouble seeing some of the detail. And I said, all you have to do is just put something over the front of it, just a piece of cardboard with a small hole, with a hole in it, a smaller hole just to dim some of the light is all it takes. You don't need anything really fancy.
Okay. Is a 100 millimeter refractor okay?
Oh, 100, yeah, that would be fine. I mean, mine's a 6 feet, and I've never had any problem with glare from looking at something like Mars. So 100 would be perfectly fine. But like I said, make sure you go out and observe. as late into the morning as you can, or decide if you're going to observe on 4 or 5 days. If you get a clear night, go at midnight one night, go maybe at 10 o'clock p.m. The next night, go at 3 in the morning the next night, so you don't lose all your sleep in one session. And if you've got, and that will give you a good chance. For those of you who are on the Halifax Center's list, Roy did send out a little thing that has some calculations involved in it. The Observer's Handbook does have a sketch of Mars showing the darker areas and the lighter areas. It has north at the bottom, I believe, and it shows the latitude, the degrees of longitude along the bottom of it. And Roy showed a simple calculation that shows how you can take the current date or the date you're not observing and convert that to tell you which degree of longitude is going to be in the center of Mars's disk when you actually look at it. And once you know that, and you know that Mars rotates at almost the same rate as the Earth, you know it's going to shift by 15 degrees every hour you watch it. So if you watch it for 4 hours, just multiply 4 times 15, that'll tell you how many degrees further on that map of Mars is going to be the area that's due south.
Okay, any other questions for Pat?
Okay.
Well, thanks so much, Pat.
Oh, you're welcome.
Most interesting and nice explanations of things that stuff I didn't know about, but then there's a lot I don't know about when it comes to planetary science, so that's wonderful.